Welcome back. This subscriber Q&A is going to be on the new million-mile battery that Tesla has announced, and whether or not this is a solid-state battery. Are we really seeing the first of the solid-state batteries to be delivered to the public? And so grab a tasty beverage and join us while we look into Tesla's new million-mile battery. All right, this video was brought to us by several subscribers that had questions regarding the architecture of the solid-state batteries. What does that look like? How does that vary between what is currently being produced and what we're going to expect to see in these vehicles in the future? And so that brings up a very important point that I need to address before we actually talk about the solid-state batteries. And that topic is the dry electrode manufacturing process. So in previous videos, I tried to make it very clear that these two technologies have nothing to do with one another. The dry electrode manufacturing process, it basically eliminates the step in making the current batteries where the materials that are put on the cathode and the anode need to be first turned into basically, for lack of a better term, a paint, and then sprayed onto the rolled material. So the problem with doing that, as anybody who will know that's worked with paint, is that it separates. You have a binder, a vehicle, a pigment, all of that in the paint that all has to be mixed together. Well, the problem is compounded when you're working with oxide materials and you're trying to make a homogeneous mix of all of your chemistry before it gets laid down. And because of that, the new dry electrode manufacturing process, where you can mix and apply these materials in a dry state, you're actually able to eliminate problems to a great degree of items settling out of suspension, and then you wind up with products that don't pass quality control. And so the two issues that Panasonic had at the Gigafactory 1 was that they couldn't meet their current manufacturing goals because of time, and they were having quality control issues. Now, the new dry electrode manufacturing process eliminates both of those issues. But I have to stress, this is at Gigafactory 1. And so while I have tried to convey that there is going to be a change in the way that Panasonic manufactures their batteries at Gigafactory 1 and potentially using this new manufacturing method worldwide, this does not relate in any way to the solid-state batteries that we're going to talk about next. And so with that out of the way, let's get to it. So, what brought this video on? Well, what brought this video on were several comments by subscribers that, that they didn't feel that what was being described by Tesla was a solid-state battery. And I came to the conclusion that I did based also on what they were saying. So that then means that what we're hearing are two different things. And so what I'm going to do now is I'm going to take you through what I hear when I hear Tesla describing their new battery technology, their new million-mile battery. But I also want to start this off by what I saw. Let's roll back the clock to the reveal of the Tesla Roadster. So what I'm going to pull up here is a image of both the Tesla Roadster and the Tesla Model S, the Roadster 2.0, obviously the new one. Now, I've done my best to try and scale these cars so that they're roughly the same size. And now I'm going to show you the battery pack. Now, one battery pack, that's 100 kilowatt hours. They said that the Roadster 2.0 is going to have a 200 kilowatt hour battery and around a 600-mile range. Now, here's two battery packs. Tell me where those are going to fit in the car. So that was my first indication that there was something else going on here with their new battery. They also spoke about the truck, and doing a little napkin drawing math, you discover that that truck is going to have a 1 megawatt hour battery. And so the weight then becomes a concern. The number of packs ultimately also become a concern, the number of actual physical batteries, because then that winds up adding to, like we said, the vehicle's weight, the vehicle's mass, but also its cost. And they were advertising the new Tesla Semi as being relatively affordable for truckers. So obviously there's something going on here. Now, this was also verified by something that I heard in the rumor mill. Now, others, this part is speculation. Again, my sources on this aren't as firm, but I'll pass it on anyway because I believe that it is in line with everything that we're learning about this million-mile battery. And that is that the Tesla Model S that they drove around the track in Germany, also in California, it weighs 350 pounds less than their existing pack. And I also firmly believe that this new battery pack also includes ultracapacitors, but we'll save that for another video. So with the clues that we have regarding the pack's physical size, now let's go ahead and take a look at what Tesla is saying. Now, the thing that I keep getting in my head as they are talking about their million-mile battery and trying to obfuscate its actual composition is one of a carnival mountebank in front of a closed curtain describing a new kind of giraffe that they have genetically engineered. And this giraffe was designed to carry heavy loads. It can, really, it's a real monster of a giraffe. And but there's some sacrifices that had to be made. The neck is a little shorter, and it lost its fur. It's kind of gray in color though, but it's got one really interesting ability, and that is that it can take 25 gallons of water into its nose now and spray it into the air. And myself and several other engineers that I had this conversation with kind of raised their hands and said, "Isn't that an elephant?" No, it's a giraffe. It's a giraffe. So now, instead of what they're calling it, let's not focus so much on what they're calling it. Let's talk about the elephant in the room. Let's talk about its capabilities. Now, the battery that they're describing is a smaller battery. It's a pouch style battery, and they showed its thermal characteristics and the number of cycles that it's capable of doing, and it didn't make any sense as far as what we've seen previously from any kind of paste type electrolyte or liquid electrolyte in these batteries. The thing that makes the batteries fail, if you haven't seen the previous videos, I'll just very quickly recap it, is that thermal stress on the electrolyte creates basically a crack in the crust that occurs in that electrolyte under normal use. And those cracks produce little spear-like structures that then dig into the electrolyte. These are referred to as dendrites, and these will eventually pierce through the electrolyte and make little shorts in the battery. And as portions of the battery start to short out, then the battery's capacity drops down. And so that's just in very simple terms, what you're looking at with a standard battery. So the first thing that caught my attention is that they referred to the new battery as a monocrystal battery. Now, here's where I have to apologize. I'm going to pull up a couple of images here. Now, when I was first looking into the solid-state batteries, the images that I got of this structure made me think initially that it was a large sheet of material that was then impregnated or doped somehow with the lithium and other materials to create the properties that we see from a solid-state battery. Well, I then discovered later that no, it wasn't actually a single sheet. It might have been formed as a single sheet, this material, but then it was broken up into granules, and then those granules were then deposited on on some kind of mastic or some other material to stick it down, maybe a glue or something. But the result is that you had a sheet of this material, this broken glass, for lack of a better term. Now, my apology is that at the time I should have saved the images of this, because though these were broken pieces, when you magnified them in, they were what are referred to as multicrystal. Now, the only example, or the best examples that I can find now of a multicrystal versus a monocrystal, or polycrystal versus a monocrystal, is this image here. Now, this is a polycrystal surface for a solar panel. Now, this was how they were done for a long time. You crushed the quartz, you baked it into an oven, and then that oven contained the doping gases. I won't go into any detail of how the silicon wafers are formed, but needless to say, you have this then fractured appearance to the surface. And that was exactly what I saw in the first images that were shown of Dr. Goodenough's solid-state battery. Okay, well, now we're hearing Tesla talking about a monocrystalline structure in their battery. And this is a monocrystal solar panel, and you can see now that you don't have those fractured areas. And so obviously, if you were to break this up, the properties might be more advantageous. I don't know. I haven't actually studied in depth this portion of how the batteries are constructed. But the important takeaway here is that we're talking about a granule type material. Now, we also need a material that can be readily manufactured. All right? Now, for that, we're going to need a lot of crystal. And how do you make a lot of crystal? Well, there's a lot of industrial ways where you can make some very large monocrystalline structures. So this crystal ball is real crystal. It was made from one of these. Now, these are gigantic crystals that are used, and they are sent to be shaped for various industries, watch crystals and all of that. Because they're grown in one piece, they retain the frequency properties that quartz crystals have. That's why they put them in watches. But the important takeaway here is that this is one way to grow large monocrystal structures. There's another way, and this other way fits neatly into the other things that I'm learning about this solid-state battery technology that we're seeing emerging, and that is spark sintering. Now, when you sinter something, you take a powdered material that then will be subjected to heat, possibly also pressure, and you can apply that heat by using a laser is fairly common. But this new technique here produces gem crystals. So the other thing that spark plasma sintering can be used for is to create monocrystals of garnet. Now, the garnet is a stone that has magnetic properties that make it interesting for a battery application. And so I believe that that's probably one of the directions that they're going to pursue. They didn't say what the monocrystal was, and so that leaves it up to us to speculate. But this spark plasma sintering already creates a monocrystal, and so then you don't have to then break it up to deposit it on a battery substrate that you'll be able to manufacture. And so this is one possible way that they are creating these monocrystals. So what are they doing with the monocrystals? Well, so here's where it gets really interesting. So when you listen to what Tesla describes their battery as, or million-mile battery as, is they said that it uses a next-generation electrolyte. Well, of course it does, because a solid-state battery has a solid electrolyte that is physically bound to the cathode side of the battery. Now, they never said that this new next-generation electrolyte was liquid. At least I never heard that that it was described as a liquid. If somebody else watching this has heard differently, I'd love to hear what you have to say about your sources of where you're getting the information that it's a liquid electrolyte. I certainly haven't heard that, but again, I could be wrong. A lot of this is speculative in nature, but it is based on what we know, what they've actually told us about the performance of this battery. And the other thing that was mentioned performance-wise about the solid-state batteries is that the batteries that were tested, lab tested by Goodenough and others, exhibited one strange thing, and that was that the battery actually became more capacious after its initial use. So in other words, a battery that would say be 200 kilowatt hours when you first got it, you'd drive it for a week and a half or so, and then all of a sudden you'd notice that the battery was 205 kilowatt hours or 210 kilowatt hours. That's just kind of an example. Don't hold me to any of those numbers. I'm just saying. The reason that I'm pointing that out is that if Tesla comes out at any time in the future and says, oh yeah, that's how these batteries respond, then you can be absolutely assured that what they're talking about is a solid-state battery. So let's close this out just a little bit by talking about vehicle performance and what we're seeing currently. There's a cute little war that just went on between Porsche and Tesla. Porsche basically decided that they were going to take a pre-production prototype version of their Taycan and run it around the Nürburgring in Germany. It's for those that don't know what that is, it's a high-speed street, basically. Very torturous road course that is used to do a performance benchmark on street cars. Because it's one thing to design a race car to drive around a race track. It's quite another thing to try and put a race car on the street with all of the potholes and uneven pavement and elevation changes. And so the Nürburgring in Germany has kind of become the de facto test course for anything that you're thinking about putting on the road. And so Porsche took one of their pre-production prototypes to the Nürburgring, ran it around, did a good time. I believe it was somewhere around 7 minutes, 40 seconds, which is quite good. And then Tesla said, hold my beer. And they sent a version of their Model S, which is a pre-production version of what they're referring to as their Plaid option. It's the car was badged as a P100D Ludicrous Plus on the back of the car, and this was also a pre-production prototype 3 electric motors. And as I mentioned before, that rumor has it that the battery that's in that car is 350 pounds lighter than the battery that's in the current Model S. Well, it's also absolutely magnificent apparently at thermal management, because that thing went around the course at 7 minutes and 20 seconds. And so, yeah, granted, I mean, they've done some suspension work on the car and wider tires. Obviously, they're going to have the plaid package as being basically throwing efficiency out the window. The people have often asked me why these electric vehicles are limited to, that kind of 150 mile per hour mark. And the reason for that is that you can design a car to be very fast, or you can design it to be very efficient, but you can't really design it to be both. Now, again, can't is a difficult word. I suppose what you could do is try and make the car so that it was able to change its aerodynamics to favor slipstreaming through the air as opposed to downforce. So I suppose that there's room for that to happen. So don't crucify me over saying that. But in general, when you're designing a car, you're either designing it to be very slippery, like the Model S and Model 3 and Model X, or you're designing it to have an incredible amount of downforce while it's driving, something like the current versions of Bugattis and all of those cars that are kind of chasing that 300 mile an hour top speed. Well, the fact remains is that if you're trying to make an electric vehicle efficient, you want to do everything that you can to shave weight. And so the end result for the cars that we'll actually see on the showroom that are not plaid are that they will be 350 pounds lighter, have the exact same range, and possibly a better range, because they will include ultracapacitors to deal with things like electric recovery braking. And currently, if you charge a Tesla up to 90% or above, you notice a dramatic decrease in the amount of regenerative braking that the car does, because it's got no place to put the power. And also over time, that if your motor overheats due to a lot of regenerative braking, the regenerative braking will also diminish in that instance. And with the addition of ultracapacitors, it will allow them to be used as a buffer. Now, in the current pack, where do you put them? There's no place to put ultracapacitors. You'd have to make space someplace else for it in the vehicle. But with a new battery architecture, one that's capable of putting the equivalent of 2 Tesla battery packs in a Roadster, well, to me, that just makes it a no-brainer that they have dramatically reduced the size of the battery packs in the batteries themselves in the battery pack. And I stand by that the only way that they're going to be able to do that is to do what they've said, and that is to produce a pouch battery. And I think that I have laid out a compelling case where that pouch battery is a solid state battery. I would love to hear what you guys have to say on that. If I've got something terribly wrong, feel free to hash this out in the comments. I think this is going to be something that we're going to have to revisit in the future. And so, until next time, if this is the kind of thing that you enjoy hearing about and hashing out, please feel free to like and subscribe. And we'll see you next time with, I'm sure, much more on this very interesting topic.